Okay, so we've been talking about continuous functions, and we want to look at one more type of continuous function, if you will, continuity of composite functions. And all of you have worked with composite functions before. If you're somewhat having trouble remembering what they are when you work with them, they're the circle things, f circle g of x, which is just f of g of x. You all know this. But as it turns out, a lot of the functions we're going to work with are going to end up being composite functions. I mean, keep in mind, even something like f of x equals 2x plus 1 squared is technically a composite function. G of x is 2x plus 1. F of x is x squared. And then f circle g of x is f of g of x, which is f of 2x plus 1, which is 2x plus 1 squared. So even that basic function is actually a composite function. And a lot of what we look at will turn out to be composite functions. And being honest, once we kind of get rid of the boring functions, we'll say, how do we make these things messier? We'll find more and more complex functions by composing one function with another. And the way it works in math is, if you're going to start creating functions out of other functions, etc., then you have to check to make sure all your definitions hold. So this continuity at a point thing doesn't work here. Will this be continuous at every single point, or will it not be? We have to mathematically define it and then check it all out. So here's where I have to make sure to use the same letters as your book. So let G be continuous at x sub 0. Let f be defined on an interval I. I want to shortcut my grammar here. So we'll say containing g of x sub 0, because keep in mind, x sub 0 is in the domain of g, then I apply g to it, which gives me, say, a y value, and f is defined on an interval around that y value, which is g of x sub 0, not x sub 0. So f is defined there, and it's continuous at g of x sub 0. Doesn't have to be continuous everywhere, only at that point. Then f composed with g is continuous at x sub 0, and the limit as x approaches x sub 0 of f circle g of x equals f of g of x sub 0. Which is, again, essentially our definition of continuity of one regular function. So we have a function g, continuous at a point x sub 0. Keep in mind, from our composition perspective, even though g is after f in the alphabet, g is actually where we start here. We pick x sub 0, we apply g to it, which then gives me, say, a y value, and then f is defined at that point and around that point. This g of x sub 0 is y. If that is true, then we'll get continuity, and this will be true. And again, using, say, the function we just had, it's pretty clear and obvious, oh, that's going to be continuous everywhere, and a lot of the polynomial type stuff will be, but we can manipulate these and make them a little bit more entertaining to see how this definition works. So suppose I have, let's see, I'll just make it up. F of x equals the square root of x minus e to the x. And actually we'll say, we'll just say, is that continuous? There's a u first. Us at x sub 0 equals 1, just so we can distinguish all my letters here. So what do I have to do? First, I have to rewrite this as two functions. So clearly my inner function, g of x, will be x minus e to the x. My outer function, f of x, will be the square root of x. Because then when I plug this in there, I get the square root of x minus e to the x, and I'm good. So now I have my composition, f circle g of x. Now I want to know if that is continuous at x sub 0 equals 1. So what do I have to do? And I know I already erased it, so we can run through it. G has to be continuous at x sub 0. So is x minus e to the x continuous at 1? Well, sure, clearly. We could graph it. We don't really have to. It's pretty obvious. That's a line. That's an exponential. Combine them, you'll still get a continuous function. So g of x is continuous at x sub 0. Put a check there. F is defined on an interval containing g of x sub 0. Well, let's see. G of x sub 0 is equal to, well, let's see. If I plug in 1, I get 1 minus e to the 1, which is 1 minus e. Those of you with calculators can throw this in to get an approximation if you want. E is about 2.7, so 1 minus 2.7 is minus 1.7. Is f defined on an interval containing that point? Well, f is a square root function. Square roots are only defined for x is greater than or equal to 0, which means f is not defined on an interval around g of x sub 0. So this function is not continuous at x sub 0 is 1. And the question would be, well, are there x's that it is continuous for? Well, maybe we'll redo this one. But we'll say, is it continuous at x sub 0 equals negative 1? Well, we check the same conditions. G of x sub 0 equals g of negative 1, which is 1 minus e to the negative 1, which is 1 minus 1 over e. And you can plug it into your calculator if you want. E is about 2.7. 1 divided by 2.7 is a decimal less than 1. So 1 minus something less than 1 is some number greater than 0, which is all I really care about. And it's definitely going to be continuous there, because this is a continuous function. What about f? Is f, let's see, defined around g of negative 1? Is it defined on some interval around that? Well, yeah. F is a square root. As long as this is greater than 0, f will be defined on an interval around it because it's defined for all the positive numbers. So this will definitely work. And since f is just the square root function, it will definitely be continuous at whatever point we get. So then this will definitely be continuous. And then we can say the composition f circle g of x is continuous at x sub 0 equal to negative 1. And again, I do stress, maybe for the last time as far as this is concerned, I'm aware that's somewhat cumbersome to do all of that just to show something is continuous at a point. Mathematically, that's kind of how we do it. So you're going to spend time just kind of running through these checklists. Is this true? Is that true? Yes, yes, no, no, etc. Okay, the last thing we want to do as far as continuity is something you've probably all seen before. It's called the intermediate, I forgot my E, intermediate value theorem. Or, in math parlance, the IVT. And I will stress, you should have seen this before, if nothing else, in 171 pre-calc. It's an incredibly important mathematical theorem. It makes a lot of what we do work. I'm going to write it out first, and then we'll just look at it. Let f be continuous on the closed interval AB. And that interval has to be closed for this to work. Let L be between f of a and f of b. Then there exists, remember backwards capital E is there exists, at least one number C such that backwards curve E, there, you see the one on top of the other so you can learn how to write them and keep them straight, okay? With A less than C less than B such that f of C equals L. Okay, and this is incredibly important, but we're not going to spend a lot of time with it. We only have a few minutes left in this video. But you have a function that's continuous on a closed interval. Let L be some number between f of A and f of B. Keep in mind, this is not A and B. It's the function value f of A and the function value f of B. Then there has to exist at least one number C with A less than C less than B. So A is in the interval between A and B with f of C equal to L, which is the value between f of A and f of B. And the idea is really quickly, suppose I have some continuous function like that. Suppose that's A and that's B. Then we'll say, we'll pretend I'm drawing more or less accurately. That's f of A and that's f of B. The function is clearly continuous and defined on the closed interval from A to B. Then there has to exist some number L, I'll arbitrarily call this L, or we'll say for any L between f of A and f of B, so I'll just arbitrarily pick this one, there has to be some C down here that maps to that point. But clearly I can just go over here, and there we go. There's C right there. And that's all the intermediate value theorem tells us, which again, seems pretty trivial and pretty obvious. Mathematically, it's incredibly important. I can also see the reflection of my video in the iPad as I videotape it, and that's not remotely drawn straight. So let me at least straighten it out a little bit right there, just so it's separate from A. Okay? But again, this idea is actually really important. You use it in 171 if you have a continuous function on some closed interval, AB, and you know that, say, f of A is -1, f of B is +1, then what has to exist between A and B? A zero somewhere. In 171, you care about finding zeros of functions, polynomials, and all that. The intermediate value theorem is what lets you do that. If nothing else, you can plot the function in your calculator and then scroll down a table and find where the function values alternate from negative to positive. And anytime they do, you have a zero for your function. So again, this is an incredibly simple, trivial little idea, but it's monumentally important. A couple of points. Clearly, for any L I pick, which is what the theorem says, I can go over and find some value down here that will map to that point. But in this case, maybe, I can actually find multiple points. The intermediate value theorem doesn't say there's only one point. It doesn't say it's unique. It says there's at least one. There might be a lot. Think about trig functions that oscillate continuously. The last thing I will say is, ultimately, as we do all of this calculus, we're going to spend a lot of time doing the algebra. We're also going to be spending a lot of time doing graphing. And understanding of graphs and continuous functions is really important. And this is what will help us on a lot of what we do. Oh, I want to graph a function. One of the things that helps me graph it is knowing if it's continuous. Another thing that helps me is if it's continuous, maybe I can use the intermediate value theorem to find zeros, and then I can get a better sketch of what the graph has to look like. And then we'll come up with some calculus ideas that will let us expand on that even further. So this is simple, I know, but it's really important. So make sure you spend time kind of pondering it and thinking about what it means.